Okay, yes. So last time we finished by introducing the notion of a category, and it's a really simple concept. So I'll just remind you quickly. A category is just objects, morphisms or arrows which go between objects. And the most important thing is composition. So a category is really defined by how you compose these arrows, right? And usually, where do we get these composition rules? We usually get them, well, we can get them, like, invent them, right? So we can say, okay, let me define a category which has just one object, okay? And just one morphism, ID, right? It has to have an identity morphism. So one object A, identity morphism on A. It's a category, right? How do I compose arrows? Well, the only arrow that I have at my disposal is this identity, and I can compose it with itself, and I will get back an identity. So the identity law will be automatically satisfied, right? And it's a good category, right? I can add another object, B, and say, okay, well, I have to have an identity for B, right? Is this the category? Yeah, it's a good category. I have composition, this ID can be only composed with this ID. This ID can be only composed with this ID. Right? This is ID B. Good, it's a category. And we can go on like this, right? But these are sort of trivial categories, and it's easy to enumerate all the composition rules for these little categories. But then we get into categories like the category of sets. And where do we get composition rules for the category of sets? Well, we create the category and we say the objects are based on, and here we sort of peek underneath and say, okay, it's based on sets. Okay? We are trying to forget about the fact that these are sets. We just call them objects now, right? But when we want to say, like, okay, we have an arrow from this object A to this object B, we can peek underneath and say, well, this is actually a function from like a two-element set into a one-element set. Okay, fine. How do we compose this morphism from another morphism? Well, we peek underneath and say, okay, if this is a function and this is a function and it's implemented this way and this one is implemented this way, then their composition will be implemented like this, and we have a name for it, it's like from set theory or from Haskell, we know this function is called this, and so on. So we do this peeking sometimes, right? But we want to, after we did our peeking, we want to have a category in which we never have to look inside the objects. All the information is hidden, and it's encoded in terms of arrows and how they compose. So this composition table, so it's like a multiplication table, but it's infinite dimensional, humongous table. We can just look at it and find out what composition is. Okay? And we know that there are simple laws for this composition. There is an identity morphism for every object, which circles back to the same object, right? And there's associativity, so that we don't have to put parentheses when we compose multiple arrows end to end. Okay. So a category really, because we are no longer looking inside objects, the category really abstracts this idea of structure. When we say that something has structure, what does it mean? Right? Usually when you say, okay, this is the structure of this organization, let's say, or this is the structure of this operating system, this is the structure of this program, what you really mean is it has components, right? And these components are related to other components. That's the essence of structure, right? And category defines structure for you. Category is just this, components, objects, and relations between these components, which are the arrows, the morphisms, right? And in general, these arrows have direction. Like this is a subsection of this section, or, this is a subcomponent of that subcomponent, and so on. And sometimes they don't have arrows. Sometimes they don't have a direction. In this case, we will think of them as isomorphisms. So we can always model the arrows that have no direction as a pair of arrows that go back and forth and cancel each other. So they are isomorphisms. So this is like a very, very general toolkit for describing things that have structure. And in particular, for mathematicians, this is a perfect tool to describe structure of their mathematical theories. Structure of an algebra, structure of topology, and so on. Group theory, they all have their structures. So when mathematicians want to talk about the structure of some theory, they can use category theory to describe that structure. But now, the interesting thing is, when you want to describe a structure that's within another structure, a substructure, right? How can you describe that? Well, since everything that is a structure is described by a category, then you are trying to look into a category that's inside another category. So how do you do this? Well, the substructure can be described as a category, and the bigger structure can be described as a category. So you have to have a way of embedding one category inside another category, or modeling one category inside another category, right? And modeling something inside something else, modeling one thing inside is a mapping from one thing to another. So we would like to be able to define a mapping between categories. And this mapping between categories would tell us how one structure fits inside another structure. So a mapping between categories would have, if we are talking about structure, we would like to have a structure-preserving mapping, right? So this structure is mapped into another structure. So a structure-preserving mapping between categories is called a functor. Okay? So let's define a functor. How would that work? So we have one category, let's call it C, and we have another category, let's call it D, right? So it will have to map objects from C to objects in D, right? Okay. So if we have an object A, let's call this functor F. This functor F maps an object A to an object FA, right? And another object B, this maps to an object FB. We're just giving a name to this, right? So a mapping of objects. In general, so we would have to define this mapping for every object in C. There would be a corresponding object in D, right? Now we want this to be sort of like a function between sets. Okay, so if the objects in C form a set, and I said before that we don't want really to say these are sets, we want to say collections and so on. But just think for a moment that this is a set of objects, then a mapping from a set of objects in one category to a set of objects in another category would be just a function, right, on the set of objects. So this function could potentially map multiple objects into a single object, right? Could squeeze stuff, right? It doesn't have to map into every object in D, Maybe it's just a subset of objects in D. That's the image of category C. So it's sort of like, embeds this whole category C inside category D. And this would be the image, right? But now, we said structure preserving mapping. What does it mean? Structure in a category is described by morphisms, by arrows. Okay? So if we have an arrow going from, let's say, from A to B, let's call it F, the functor would also have to define what it means mapping an arrow, right? Not only mapping objects, but also mapping arrows. So if we have a morphism from A to B, we would want this to be mapped into a morphism from FA to FB, right? So if these two things are connected in this category, we want them to be connected in the image as well, right? So every morphism here is mapped to a morphism. And we call this morphism here F acting on F, okay? So a functor is really two mappings. Okay? You have to define separately these two mappings. One, how do you map objects? And two, how do you map morphisms between these objects? Okay? And of course, a morphism between A and B cannot be mapped into a morphism between some arbitrary objects. Here, we want it to be a morphism between the images of these two objects. It kind of makes sense, right? So in this way, we are embedding this whole structure inside the category of D, and we are embedding all the objects and all the morphisms, right? And again, because this is a function on arrows, on morphisms, it can map multiple morphisms here into a single morphism here. It's okay. It can squish things together. It can squish objects. It can squish arrows together, right? And it can leave some arrows out here. So not everything is covered by the image of this category. So you have to keep in mind these things, that it's not a one-to-one correspondence. It could be losing some information, okay? So we always deal with these things that lose information in mathematics. We start with functions. Functions can also squeeze things together, and they don't cover the whole image. So they are like information-losing things. Functors are also these things that might lose information. And now, when I say losing information, it might sound kind of negative, like, oh, okay, why are we dropping information? We should be like holding every single piece of information close to our hearts, never lose it, right? Well, it turns out that losing information has a very positive spin on it, because we can call it abstraction. When you abstract things, right, you lose some information. You say, this information is really not that important. I want to get rid of this additional detailed information. I want to have the big picture. And the big picture you get by just dropping some information. And suddenly you see similarities between things, because if you drop the inessential details, then suddenly you see that they are similar, right? It's like seeing the forest behind the trees, okay? So this is what a functor is. Well, not really. I forgot about something, right? When I say preserving structure, the structure of a category, right? Here we see this category. So objects, yes. We have a mapping of objects. Morphisms, we have a mapping of morphisms. What about composition? Okay, so a functor, if it's a good functor, it has to preserve the structure, meaning it has to preserve the composition. So if a functor if we apply a functor to a composition of two morphisms, right? So let's apply functor to G after F, okay? Then we should get a composition of images of F and G. So it should be F acting on G after F acting on F, right? Which means, well, this is a small picture, so so I always end up extending these pictures. So let's say we have another morphism G here from B to C, right? And here we extend this. C goes into FC, right? This is FG. It's getting a little messy, right? But the important thing is that when you compose G after F, you get this one arrow from A to C. If you compose FG after FF, you get this one arrow here. And these two arrows should be the same. Okay? So this is preservation of composition. Right? So a functor must be such a mapping that preserves composition. What else do we have? Oh, identity. Well, a functor acting on an identity, FIDA, should give us an identity on this side. So it would give us an identity on what object? On the object FA. Right? So it takes an identity from here, maps it into an identity here. Okay? And finally, well, it should preserve associativity, right? So, no, actually it doesn't have to, because associativity will automatically be preserved, right? Am I right? Okay. But you've heard of functors before, right? Because people use functors all the time in programming. Now even, people who program in C++, they know what a functor is, hopefully, Java. It may be hard to express it in a very generic way, but it's possible. So, so what we call functors in programming comes from category theory, but it's a little bit simplified, because let's just concentrate on Haskell. In Haskell, we just deal with this one category of types and functions. So types, objects, functions, arrows. Okay. So because we have this one category most of the time, I mean, it's possible to also figure out, embed other categories inside of Haskell. But for now, it's just say we had just one category of types and arrows, and types and functions. And let's just have functors. So the functors will just map this category to itself. So D is the same as C, and it's the category of types and functions. It's okay. It's just, you have this big picture, but you can always shrink this picture to a single category and say, I'm mapping this category into itself. So let me give you an example. And these are called endo functors. Endo functors are just functors that are from the same category into the same category. So let me give you an example of an endo functor in Haskell. So for those of you who are not really into Haskell very much, this should be kind of self-explanatory, because Haskell syntax is pretty simple. So let's say the maybe functor, okay? So it's a data type called maybe. and it's parameterized by type A. So it's a generic type. So like in C++, you would say this is a template of class A, right? So A is this parameter, type parameter. And it's defined as a sum type, so it's nothing or just A. In other languages, people call it optional or option. You know, it always has this like sort of if you have a function that doesn't always evaluate the result but sometimes fails, then it's implemented as a function returning an optional thing, right? So if it cannot calculate something, it returns nothing. But if it can, then it returns just this A. Okay? So how is this a functor, you might ask? Well, so functor consists of two things, right? Mapping of objects and mapping of morphisms. So this is a mapping of objects. It takes an object A, type A, right? And maps it into a new object called maybe A. This is a new type. This is a type called maybe A. So it's a mapping from A. I'll need this picture somewhere here. So it maps A into maybe A. But there's the second part, right? So it has to map also functions, right? So how do you map a function? So let's say we have a function that goes from A to B. Okay? So we have a function. Okay, actually, I want to draw this vertically and this horizontally because we call it lifting. So maybe A will be here, right? So A is mapped into maybe A, and we have a function f that goes from A to B. Now B is mapped into maybe B, right? So this is like this is this is where the functor will takes this picture into this picture, right? So it takes A into maybe A, B into maybe B. It has to take F into, well, sort of like a maybe F, right? Let's call this is called F map in Haskell, F map F. Okay? So how is this F map F defined? Well, it has to be defined separately. So it maps maybe A into maybe B. Maybe A is of the form either it's nothing or just A. So we can define this F map acting on nothing, and we can define this F map acting on just A. So what should it do on nothing? It has to return maybe B. So F map F. It takes F as an argument and then acts on this maybe, right? So on nothing, the only thing it can do is return nothing, right? Because it doesn't have anything to work with. I mean, it can either return nothing or just, but just what? It doesn't have anything to return, right? On just A, we define it as returning F acting on A. Okay? And that's the definition. So F map is this part of the functor that works on morphisms. Okay? So this is an actual functor, Endo Functor, right? But it's a functor. So usually people concentrate on this part, right? But remember that a functor has two parts. This is the first part of the functor. It's called a type constructor, which is a mapping of types to types. Okay? So it's kind of very non-symmetric picture in a programming language, but in category theory, it's just part of the same thing. mapping on objects, mapping on morphisms. Okay. Now, the way to get some feeling for what a functor is in a programming language, it's nice to think of a functor as a container of things. So maybe is just a very simple container. It's a container that may contain nothing, so it's empty, or it just contains a single value of type A. Okay? But it's a universal container. A is here a universal thing. It's not. It can be an integer. It could be a Boolean. It could even be another maybe. It could be a list. It could be a function. Whatever you put into it is okay. So this is a polymorphic type. It's called a polymorphic type, right? Another example of a container, a list, right? A list is a container of things. So a list is a functor too. You can, I mean, everybody who programs in Haskell knows that, you know, an fmap for a list is just a map. So you just apply the function to every element inside the list. That's how you operate. So this is how you lift a function to act on lists. And so on. Okay? A tree is a functor. So all these data structures that serve as containers are kind of easily understood as functors. And it's very easy to implement fmap for them. There are some other functors like the reader functor or the writer functor that are based on functions as containers. And it's maybe a little bit harder to understand them as containers, but it's also, I think it's a very useful abstraction. Yeah? Mm-hmm. Okay. Okay, that's a very good question. What if I misdefine fmap? Is it possible that I can define fmap and it's not really a functor, right? So yes, it's possible because in this language, in Haskell, there is a part of the functor that is expressible, that I can express, right? There is another hidden part of the functor that I can express in category theory, but I can't really express in Haskell, right? That's the laws, right? So, like, does it really take an identity into identity? Does it take composition into composition, right? It's not obvious. So actually, well, let's check. Because there is a way of doing this in Haskell. It's called equational reasoning. So it's sort of like you cannot really execute this. You cannot implement it in Haskell. But you can use Haskell notation to reason about Haskell programs, right? So let's try to reason about this. And reasoning in Haskell is based on replacing things with equal things, right? So like when you have a definition of fmap or you have a definition of a data structure, you can always replace one thing by another, right? So we would like to show, for instance, that fmap takes identity to identity, okay? So fmap ID. So we have to test it for these two cases, nothing and just, right? So does it take nothing? So what should it do? It should take ID into ID. So it should take nothing into nothing, right? Because ID acting on nothing gives us nothing. So let's check equational reasoning. F map F of nothing equals nothing. And it actually does not depend on F. So on ID will act the same way. So F map of nothing is nothing, which is the same as ID acting on nothing. So that works. That part works. Okay. What about F map ID acting on some just A? Okay. Okay, equational reasoning. F map F of just A is equal, right? So in Haskell, actually, this equality means you can substitute this for this or this for this, because you can substitute equals for equals. Okay, so I can substitute this with this, replacing F with ID. Okay, so this is equal to just F replaced with ID A. Okay. Now ID A, okay, I would have now to look at the definition of ID. What's the definition of ID? ID A equals A. That's the definition of ID. So I can replace ID A with A, right? So it's just A. Now I can use this backwards, and I can say, okay, just A, replace A with just A. Just A equals ID just A, okay? So it's ID of just A. So ID was F mapped to ID, okay? And you can do the same kind of reasoning for composition. That a composition goes into composition. Again, by cases. You do it for nothing, and you do it for just. And you just replace things, equal things with equal things, and you get it. So people usually don't do this unless they suspect that something might be a little funny, right? So it would be a good exercise to say, well, okay, what happens if I put nothing here, right? Will something go wrong or not? Probably something will go wrong with identity. Huh? I suppose, yeah. Okay. So equational reasoning, very important thing. You can't do it in any other language. Okay, this is only in Haskell you can do this. Okay, so the next thing I want to talk about is natural transformations. So if you have this image of a functor as modeling one category inside another, just think of this first category as being something small, some small diagram or something, and you embed it into a bigger category. So you are modeling this thing inside a bigger category in much bigger context, right? But maybe there are more than one way of embedding this category, right? So what does it mean? It means that you can have multiple functors going from this category. Let's call it C. And we have category D, right? I tried to make it bigger because I know I will need more. Okay, let's make it really big. Okay, so we have one functor that maps this object A into, so let's call it Fa. Okay? But we also have another functor, G, that maps this object into GA. Okay. And in fact, this functor f maps this whole thing into some subcategory here, and this whole category C into some subcategory G of C, right? So we have embedded this category or modeled this category C inside D in two different ways. And now we are interested in the question, what's the relation between these two embeddings, or between these two models, right? So in order to understand the relation between these two models, we would like to define some kind of structure-preserving mapping between these two models, okay? So in other ways, we have two functors, and we want to define a mapping between two functors. So, obviously, part of this mapping, right, should be a mapping of objects. So if we have an object A in this category, then we have these two objects. Now we have two objects in this category. So if we want to map the model that's given by F to a model that's given by G, we want to have a mapping between these two models now, right? So this, and we want, where can we get these mappings from? I mean, this is a category. So in a category, we have morphisms. So we pick a morphism here in this category as this component of this transformation. So we're transforming one model into another, right? And we are now zooming in into one tiny part of this model that was obtained from A, and one tiny part of this model that was obtained from A. And we want to find a morphism in this category that goes from FA to GA. Okay? And we have to do this for every object. So there's an object B here, right? And it will map, F will map this into FB, and G will map it into, let's see, I want to have a big picture here, GB, okay? So now we have another little part of this model, right? That's generated by B. Here's FB, SGB. So we have to have, if we want to compare these two, we have to find a morphism between FB and GB. And so on. For every object in C, we have to find a morphism here, right? So these morphisms will form a family, a whole huge family of morphisms that is indexed by objects in C. So we'll call this family, let's call it alpha. So this is a component of alpha at A. This is a component of alpha at B, and so on. So it's a whole huge family of morphisms in category D, right? For every object in C, we have a morphism in D. So that's an interesting new thing, right? It's like it's mapping objects into morphisms now. Okay. So, but what does it do to morphisms in C, right? So C has a structure, right? So let's see. There's a function. There's a morphism F going from A to B. Well, so what happens is that F is already mapped by both F and G because these are functors, right? So functors map morphisms as well. So functor F will map this morphism into a morphism from FA to FB, right? So this is F acting on little f. and functor G will map the same morphism into a morphism going from GA to GB. So this is GF. Okay? The same F was mapped in two different ways. So we already sort of have the mapping of morphisms. The only thing that we can require is that these mappings are compatible, that whatever the functors are doing with this morphism is compatible with whatever the natural transformation is doing. Which means we want this square, well, this square, okay, we want this square to commute. What does it mean? It means that there are two ways of going about it, right? So let me just redraw this nicely. This is FF, this is FB. And this is alpha A going to GA, right? This is GF. This is GB. And this is alpha B. Right? So I just redraw this diagram so that it's more square looking, right? Okay, let's say this is a square. Okay, so there are two ways of going from FA to GB, right? You can do first go FF and then follow it by alpha B, right? So alpha B F FF. And there's another one. You can go first alpha and then use the functor. And we want these two to be equal. So this is GF after alpha A, right? So this, you can look at this equation as relating alpha B to alpha A. It's like sort of like transporting alpha. So this is a very strong requirement for a natural transformation that actually, in some cases, it even gives you alpha B in terms of alpha A. In which case, if one of these were invertible, then you would just get it, right? So this is called the naturality condition. And of course, natural transformation is something very special. It doesn't happen often, right? In most cases, you won't be able to find a natural transformation between two functors. It's not given, right? I mean, look at this. We said you have to pick a morphism. For every object, you have to pick the morphism from this particular Hom set. You remember what a Hom set is? It's a set of morphisms between two objects. So from each Hom set here, you have to pick a morphism. What if this Hom set is empty? Some Hom sets are empty. Well, maybe not in set, because there are like lots of functions from every type to every type. But in some other categories, there might not be a morphism even. So that already precludes the existence of a natural transformation. And then once you pick one, then the choice of the next one is really constrained by this naturality condition, right? So natural transformations are special. So what is a natural transformation in terms of a programming language, in Haskell, for instance? Well, it's a family of functions, right? Morphisms become functions that's indexed by an object or type, right? So in this case, these functors would be Endo Functors, right? Within the same category. That's okay. But it's a family of functions that's called a polymorphic function, right? So natural transformations are expressed as polymorphic functions. Now, most interesting polymorphic functions in Haskell will actually be natural transformations. And what does it mean? Okay, so let me write the formula. So this would be a natural transformation would be of the type, if you have functor f, then it's a family of functions from functor fa, from fa to ga, right? Now this is not Haskell notation, but just for, okay, just for your information, right? I mark it as a component of alpha at a. But it's a polymorphic function, right? It takes fa to ga. F is one functor, g is another functor. So you can pick, for instance, as the first functor, let's say a list functor, right? So you can have a natural transformation from a list of a's to, let's say, maybe a. Or you could have a natural transformation from a list of a to a list of a, right? And so on. I didn't give you many examples of functors, but these are, so I cannot really write a lot of. Then there are some, well, there is an identity functor, so every time you have, you know, a list of a to a, for instance, this is just identity functor. It just doesn't change anything, takes an object and maps it into itself, and takes a morphism, maps it to itself. So anything like this is also a natural transformation. And then you might ask, okay, so you would probably ask this question, right? What about the laws, right? So if I define a natural transformation as a polymorphic function, do I have to check this condition? Because it means f map f, you know, it's like alpha after f map f must be equal to f map f after alpha, something like this, right? So, good news is that it's automatically satisfied in Haskell. Why is it automatically satisfied? Because when you write a polymorphic function in Haskell, you're not really, you're very much constrained by the language. The language says if you want to write a parametrically polymorphic function, it means it has to have use the same formula, the same expression for every type, right? So if I define this function, I cannot say, okay, I define this function differently for integers and different for booleans. It has to be the same formula, right? That's called parametric polymorphism. And because you impose this parametricity, because you have to use one formula for all components of your natural transformation, it follows then the naturality condition is automatically satisfied. So that's the beauty of system F. Okay. So the final thing that I want to say, so this is like the technical part of this is done, okay? But now the concepts behind this. So natural transformations are just transformations, okay? So these are mappings from one functor to another functor. Are these mappings composable? Can we compose these natural transformations? And obviously, we can compose them, because if you have a natural transformation from fa to ga, right? This is alpha a. And then you have another transformation, beta, that gives you some h of a, right? So if you have three functors, right? and you have a natural transformation between F and G, and you have a natural transformation between G and H, right? Then the components of these natural transformations for A are just two morphisms, right? Morphisms are composable, right? So you can compose these morphisms, therefore you can compose natural transformations. This is like a very simple composition rule, right? So you can compose natural transformations, and so they are composable. Is there an identity natural transformation, maybe? Of course there is. An identity natural transformation would just like go back, from FA to FA, right? And you could just use ID A as a component at every A, right? So an identity natural transformation is trivial. Between every functor and itself, there is an identity natural transformation. So we have composition, we have identity, right? You can easily convince yourself that this is associative, this composition, right? So there is a category there, right? What is this category? Well, it's a category in which objects are functors, right? Are functors between some categories C and D, right? And morphisms are natural transformations. Okay? And we just got ourselves another category. It's like once you know about categories, they are everywhere. Anytime you have some transformation that has a composition, that transformations usually are composable, right? So every time you have a composable transformation which has an identity, you have a category, right? You might not have known that you had this category, but you do, right? So this is called a functor category. A functor category between two functors. Between two categories C and D, right? So there is a notation for this, very simple. Mathematicians are very terse in their notation. So this is called a functor category between C and D. Okay? So how much time do I have? Over? Okay, so we have a functor category. But did I mention that functors also compose? Right? What's a composition of two functors? Well, you just compose them on objects, and you compose them on morphisms. So functors do compose. So you can take a functor after a functor, right? Easily. So like if you have functor F acting on some object A, it gives you an object. So this, if A is in category C, FA is in category D, and if you have functor from D to some E, right, then you can compose them. Right? So you have category C, a functor F to category D, you have functor G to category E. You can compose them this way. Okay? And the same for morphisms. So functors are also composable. And is there an identity functor? Obviously, I already mentioned that, a functor that just takes an object into itself and morphism to itself doesn't do anything. It's an identity functor. So functors also could be morphisms. But in what category would they be morphisms? Well, what are the objects here? Categories. Okay? So there is a category of categories. called cat, in which objects are categories and morphisms are functors. Okay? So yet another category. Now, of course, I have to be very, very careful here because if there are mathematicians here, they will try to kill me now, right? Because what about the size of this category, right? It's like it would be a category of, it's like the set of all sets. The problem of category of all categories doesn't make sense. So usually people avoid this by saying we'll have a category of small categories. Small category means a category that has objects, that objects form a set, and so on. So, you know, just keep this in the back of your mind that, you know, like everybody should be careful about how big certain things are, that they can actually spill out of sets. But there is a category of small categories, and that's what it is. Okay, so we have talked about a category of categories, and we have talked about category of functors. Functors form a category. We have a category of sets, right? And we have a category of types and functions. So that should be enough for you till tomorrow. Okay, thank you. Any questions? Okay. You want to record? I can repeat the questions. That's another way of doing this.
So you're going to mention the infinity categories more?
The infinity categories.
Over there.
Please put it here, right? Yeah, if there is a demand for infinity categories and infinity groupoids, yes? Is that what you want to hear about? Infinity groupoids? Yeah, yeah. I might go in this direction a little bit because since I want to talk about type theory, so that naturally leads to homotopy type theory, right? And in homotopy type theory, you have these infinity groupoids. And we are like one step from here to groupoids, yeah. Yeah, so yeah, I can talk about this. Mm-hmm. Okay, anybody else?